Hi, this is an example problem from Chapter 31 on balancing nuclear reaction equations. We're going to be looking at three different examples of radioactive decay, which is a form of a nuclear reaction where you have nuclei are changed from one state to another, or one type of nuclei to another. And so we're going to go ahead and learn how to write those reactions and balance them. Let's quickly look at some notes here. So conservation rules for balancing reaction equations, a couple things that you want to look on both sides of the reaction: that the total mass number A is the same, the total electric charge on both sides is the same, conservation of charge, and the third one is lepton number. This one's a little bit different, it has to do with neutrinos and electrons, positrons. 1 and 2, the most important ones. So let's go ahead and look at the different types of radioactive decay. There's three types. You can have a nucleus spit out three different types of particles and leaving the nucleus transformed. One is a alpha particle, which is a helium nucleus. Another one is a beta minus, which is an electron, or you can have a beta plus, a positron, or you can have gamma, which is just a high energy photon. In this case, the nucleus doesn't change its Z or A number. It just goes from a excited state to a relaxed state, just like emitting a photon for a electron transition, but this is for the nucleus. So let's look at a couple of these processes. First one we have is alpha decay, and that's what the first one looks like here. So let's go back and look at this. Plutonium-242 Pu, right, undergoes alpha decay. Well, we're going to go ahead and write down what the reaction equation is and identify the daughter here. So we want to look at the general form of a alpha decay. Let's go look at it here. Here's the general equation here, and we're going to go ahead and copy that real quick. So we typically kind of call the original nucleus on this side of the equation the parent. And after the reaction, you are left with a alpha particle, a helium nucleus, which is ejected from the nucleus. And then you have a daughter nucleus also. And so we're trying to find the daughter here. Notice that in the general equation, if you look at, if you add up the mass number, A minus 4 plus 4, you get A, so those are equal. So that conserves mass number. Similarly, if you add up the number of protons, Z minus 2 plus 2, that gives you Z, so we've conserved charge here as well. Same number of protons before and after. All right, so now we're going to go ahead and write this generic form here with the actual nucleus. So we've got plutonium, actually I don't know what that is, Pu, 242, and again 94 Pu. Those are the same, so it's kind of redundant in a way. And we just follow the formula here. 242 minus 4, that gives us 238. Z minus 2, 94 minus 2 gives us 92. We need to identify what that is. Don't know what it is yet. We'll look it up. And then, of course, we've got the helium, the alpha particle. So to determine what this daughter is, we'll just go to the periodic table and look at the element that has 92 protons. So let's see here. Looks like we're down here in the actinide series. 92, it's uranium. And there was Pu there. That might be plutonium. There we go. So it's uranium. So that's our daughter, uranium-238. And, well, of course, that was plutonium. It's written up there. And that's the alpha decay for that. Let's look at part B here. In this case, we have sodium, 24, which undergoes a beta minus decay. Let's go ahead and look up that reaction equation. So beta decay is, again, as I said earlier, there's two types, beta minus, beta plus. Beta minus is the emission of an electron. And let's go ahead and copy that equation, and we'll paste it in there. All right, so here we have it. We're going to start off with our parent here, which is sodium-24. 11 protons. for sodium. And again, just to verify, right, so because we're adding we're ejecting an electron, there's your -1 charge. We need to add to the number of protons so that when you add Z plus 1 plus a -1, you end up with just Z. And so that works. Now the third one, the third conservation rule is this lepton number. And it turns out when you make an electron and that you need to get this antineutrino to balance those two things cancel. So don't worry too much about that, but that's just what the equation looks like. It's an additional conservation rule for nuclear processes. And in this case, we're going to go ahead and figure out what the next one is. So it's going to be same atomic number, 24. Z plus 1 becomes 12. We got to look that up. And of course, we also get the electron, -1 charge, 0 nucleons, and the antineutrino. This bar on the top means that it is the antiparticle. All right, let's go back to our periodic table and see what has 12 protons, which element that is. Again, this is the periodic table from the back of your textbook in the back matter. You can look it up. And so here's sodium, and so 12 is going to be magnesium. In this case, here's our daughter. All right, and finally we got one more to go here. Okay, part C. Here we have nitrogen 13, and it undergoes beta plus decay. Let's go look up that. So the beta plus here, instead of emitting an electron, it emits a positron, which is the anti-electron, and that's why we have a bar on the top, and it emits a neutrino as well. So let's copy that and paste it in. So here we're going to begin with the parent nucleus, nitrogen 13, and the reaction is going to give us a 1 less, going to be 6, and the atomic number is the same, 13 plus a positron and a neutrino. And 6, I think that's carbon. Let's go look it up real quick. Yep, carbon, there we go. And so there is the daughter for this process.